Hello, this is a Math 311 Linear Algebra lecture on Section 1.2, probably the part 1 of Section 1.2, which is about the length and angle of certain vectors, and importantly the dot product. We're going to find what the dot product is, how it's computed, but also why it's so useful. Well, I will just say this before we get started. I am going to ask you to look at Theorem 1.1 in the text on page 10. It basically talks about the algebraic properties of vectors. Basically, it says u plus v is equal to v plus u. I didn't really want to write them out, especially since they're in the book. They seem to be pretty apparent. I think there are maybe a couple proofs there. You don't have to really know them, but I would like you to look at those anyway. All right, so today, as I said, we're going to be talking about length and angle in regards to vectors. We know we're going to find out that every vector has a length, and then we can talk about the angle between two vectors, specifically what is it and how do we measure it. So to start off, let's recall the distance formula. Okay, in two dimensions, we know that if we have 2 points in the xy plane, we can compute their distance using this formula. Basically, we take the difference in the x coordinates, square them, the difference in the y coordinates, and square them, add them together, and then take the square root. Okay. Now we can view this either as the length of both the length of vector AB or the vector BA. We can see that it really doesn't matter which direction it is, that length is kind of independent of direction. And that's because we can interchange x1 and x2 and y1 and y2, and because we're squaring this, the sign doesn't matter. Okay, so that's the distance formula, and that gives us the length of these vectors. That's how we actually can compute, AB to be this vector and BA to be this vector, and then we get this distance. So how can we generalize this to points and vectors in Rn? Well, we define the length. Remember, a vector in Rn consists of n components. Okay, so what we're going to do is we are going to square all those components because they're just real numbers, add them together, and take a square root. Okay, so we're just doing this where we're replacing with. In the previous case, we had n equals 2, and we're just going to add up all the squares and take the square root. Obviously, we don't have to worry about taking the square root of a negative number because all of these squares in here are going to be non-negative, right? Okay, so what is going to be just some examples here? And notice we have this sort of double absolute value sign to denote the length. So in this first example, for u, the length of u is going to be the length of the vector 3, 2. So this would be 3 squared plus negative 2 squared. It's going to be the square root of 9 plus 4, the square root of 13, right? Okay. And then we have the other one. The v is going to be a vector in 4 dimensions. Now this would be 1 squared plus negative 4 squared plus 2 squared plus 5 squared. That will be the square root of, if my arithmetic is correct, 1 plus 16 plus 4 plus 25. And I think this turns out to be the square root of 46, I hope. Okay. And we're just going to leave this here. We're not going to really worry about, simplifying square roots, because that's not what this course is about. All right. The first theorem of today isn't really that big a deal. It's a theorem. Says that if remember what this means is if C is an element in the real numbers, basically if C is a real number and V is a vector in Rn, then the only way the length can be 0 is if the vector is 0, and vice versa. Remember, if and only if says that if one of these is true, then the other is true. So it means that this implies this, and this implies this. One thing to keep in mind is that I put a hat over this 0, but not this 0, and that's because that this is a number. It's a scalar quantity, okay, whereas this is a vector quantity. Also, if we multiply a vector by C, the length of the resulting product would just be the absolute value of C times whatever the length of V is. Okay, and to prove this, we're not going to be that big on proofs in this course. You're not going to necessarily have to reproduce them, but I just want to show you. I still want to show you these proofs to show that we're not making these up, right? That these follow logically from the definitions. So, how do we do that? I'm just going to prove the second part, part B. And just remind that, so if V consists of the vector V1 through Vn, then CV is CV1 through CVn. Okay. And so the length of CV is the square root of CV1 squared plus CVn squared. Oops. And then we can factor out the C squared, right? This will be C squared times V1 squared plus dot 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 plus Vn squared. Okay. And this will be the square root of C squared times the square root of V1 squared plus Vn squared. And this is going to be the length of V. And this is the only tricky part. The square root of C squared, that's not C, because if C is negative, this is always positive, and C could be negative. So in fact, this is the absolute value of C. So that's why we have that. Okay. All right. Part A is even easier if you just go through think about it. Basically, because the only way that this stuff could, under the radical, could be 0 is if all these squares are 0. Okay. All right. Now there's a special type of vector which is called a unit vector, and all that is a vector of length 1. And this holds even, no matter what. We can define unit vectors in all dimensions. Okay. So these are all unit vectors because their length is 1. We can see that 1 squared plus 0 squared is 1. Okay. Similarly, 0 plus negative 1 squared. Okay, that's going to be 1. If we square these two, we get 1/2 plus 1/2. That's 1. If we square these, we get 1/6 plus 1/6 plus 4/6. Okay. So, and of course, so that now what I've written here obviously is the square of the distance, but then if the square root of 1 is just 1. So these are all unit vectors. Now, as soon as we have a way of measuring the length of a vector, we can talk about the distance between two vectors, because the difference between them is itself a vector. And in fact, we define the distance between two vectors u and v just to be the length of their difference. Okay, so in this next example, if we wanted to find the distance between these two vectors u and v, we could compute u minus v. Okay, so that would be 1 minus 2, negative 1 minus 1, and 3 minus 6. And that, I think, is negative 1, negative 2, negative 3, right? Okay. So, and then when we take the length of this, square root of negative 1 squared plus negative 2 squared plus negative 3 squared, which is the square root of 1 plus 4 plus 9, which is the square root of 14. Okay. Okay, you'll see a lot of these distances and lengths are going to be square roots, of course. Okay. All right. So, and one other thing, I think this is more or less obvious, hopefully. The distance between u and v and the distance between v and u are, of course, the same because, you know, this is we're taking a, well, it just is. All right, we can change the sign of the components, but when we square them, they go away. Distance is always going to be a non-negative number, and the only way that this can be 0 is if u and v are exactly the same. Okay, hopefully that's more or less obvious. Okay, now let's talk about the non-obvious part of today's lecture. And we want to talk about angles. Okay. Question is, so the question becomes, how do we measure, or how do we define an angle between two vectors in Rn? That can be especially interesting when we can't comprehend like something beyond four dimensions, like or you know, if you how do we really talk about an angle between two vectors in, let's say, 5 dimensions? Well, one thing, the idea is that if you have two vectors, if you think the vectors as directed line segments and lines as just one-dimensional things, so you can think of like two lines coming together and forming a plane, or some will say something two-dimensional. We haven't defined any of these terms yet, so don't worry. But if you can sort of embed these two vectors in a plane, and then reduce everything to the R2 case, then you can draw maybe you can draw a triangle, complete a triangle, and find the angle of this, whatever is over here between them. Okay, now let's just focus on what happens in R2, because we're familiar that hopefully we remember some of this stuff from trigonometry. So here we have an angle. We can represent them as vectors. We take the triangle generated by these two vectors, u and v, and then this vector is u minus v. And we can if we just treat them as a regular triangle and call this length a and this length b and this length c. So a is the length of u, b is the length of v, and c is the length of u minus v. Now, if you remember the cosines, which I most certainly do not, and most people who are not teaching math or taking math or trigonometry kind of tend to forget this. But the law of cosines says that if c is the side opposite the angle, and c squared is a squared plus b squared minus 2ab cosine theta. Okay, we know that from trigonometry. Now, let's see where this goes, all right? If we take, just replace, making these substitutions here, then we get the square of the length of u minus v is equal to the square of the length of u plus the square of the length of v minus 2 times the length of u times the length of v times the cosine theta. Okay. All right, now let's go back and unravel these definitions, because this, after all, is u minus, the length of u minus v is going to be u1 minus v1 squared plus u2 minus v2 squared. Okay, so that's this side. You'll notice that this is the length. When we square the length, the square root goes away. And then similarly, this is going to be u1 squared plus u2 squared. And then this is going to be v1 squared plus v2 squared. And then we have minus 2 times the length of u times the length of v times cosine theta. All right. Now, if we multiply this out a little bit, this is going to be u1 squared minus 2u1 v1 plus v1 squared plus u2 squared minus 2u2 v2 plus v2 squared. Okay. And then you look at this side, and you see there's a bunch of things cancel out. The u1 squares cancel, the v1 squares cancel, the u2 squares cancel, and the v2 squares cancel. Okay. And then everything else is divisible by -2, so we can divide by -1/2. And what we get, amazingly, is u1 v1 plus u2 v2 is equal to this product of these square roots times cosine theta. And we don't really have to worry about these being 0. If they're 0, there's really no sense in talking about an angle between them. So we can divide by both of these, and we get that cosine of theta is going to be u1 v1 plus u2 v2 divided by this square root times this square root. Okay. And what the thing here is that this is completely in terms of our coordinates. Okay. Once we understand the cosine, as long as we restrict, our angle to be between, 0 and 180 degrees, this cosine determines the angle, and this cosine is completely determined by the coordinates. Okay. Now the question is, well, that's for n equals 2. What happens when n equals 3? What is the most obvious generalization of this? Okay, well, we could say, we look at this quantity, and instead of adding one more dimension, we get u1 v1 plus u2 v2 plus u3 v3 over this square root. Okay. Now, could we use this? This is certainly is a real number that would be defined given two vectors in R3. And the thing is, can we use this to describe the cosine of the angle between two vectors in R3? And then, of course, we could also generalize this to R4 and other dimensions. Okay. Well, that looks like it might work as long as this is between 1 and -1. Okay, that's not quite obvious why it should be. And in fact, it's not obvious, because we need it to be, because the cosine of anything has to be between 1 and -1. All right, so that's going to be the next thing we have to check. That's why we have, in your notes, we have, well, the Cauchy-Schwarz inequality. But let me just, before we do that, let's talk about this. If you look at this expression and this expression, that should be look a little familiar to those of you who have had multivariate calculus. Okay, it's obviously the dot product, and that is where the dot product just has its value. It's why it's useful, because it's going to be a way of measuring the angle between two vectors. Okay, because these other quantities down here, those are just the length of vectors. Okay, we know what those represent. So it's the dot product which really gives us a sense of angle. So that's why we define this dot product this way. We say if u and v are two vectors in Rn, then we define the dot product of u and v to be u dot v equals u1 v1 plus u2 v2 plus ... plus un vn. Okay, this is always going to be a number. Okay, it's a scalar quantity. So, for example, this is pretty easy to compute. The dot product of these two vectors would be 4 times 6 plus -7 times 1, which is 24 minus 7, which is 17. These vectors in 3 dimensions, this would be 1 times 1 plus -1 times 2 plus 3 times 6, which is 1 minus 2 plus 18, which is negative 17. I didn't really I didn't pick these for these to be opposites. They just turned out that way. And then if we take the dot product of these two vectors, this is just nonsense because they're of different lengths, different dimensions, right? Okay, this is an R3, this is an R2, so this is nonsense. Okay, nonsense, or we should say undefined. Okay, so they have to have the same number of components for you to take the dot product or to do anything else with them. Okay, there are the properties of the dot product are given below. If we have vectors u, v, and w in Rn and a real number c, I think we can see what the u dot v should be v dot u. Obviously, we can we can multiply these in any order. That doesn't matter. Number 2, that this is really just a case of the distributive law. Okay. This is also sort of a case of a distributive law where you can factor out a c. Okay. For u dot u, this is basically just sort of what we talked about before. If we have a sum of a bunch of squares, the only way that they can be 0 is if all of the squares are 0. Okay, so we have u dot u is always going to be greater than or equal to 0. And then turns out, of course, that the dot product of u with itself is in fact the square of the length. Okay, because remember that u is going to be u1 squared plus u2 squared. Okay, and then this thing right here is just u1 times u1 plus u2 u2. Okay, so it's a dot product of u with itself. And then if we just replace u with u minus v, we get number 6, which says the square of the distance between two vectors is going to be the dot product of u minus v with itself. Okay, and that's going to be pretty important here. So those are the properties of the dot product. Okay, I didn't really sketch out a real detailed proof of this because hopefully maybe you've seen these before in calculus, and even if you didn't, it's hopefully these are pretty apparent just from the way this is calculated or how it's defined. Okay, now I want to go back to this whole question about if we want to use so obviously in this case this was a dot product of u and v, okay, and so is this one here. And in fact, we can see that the cosine appears to be defined as the dot product of u and v divided by the length of u and the length times the length of v. Okay. Now we want this to be a cosine of an angle, but it can only happen is if this fraction is between 1 and -1, which means that the absolute value of the numerator has to be less than or equal to the absolute value of the denominator. Okay. In other words, we need the Cauchy-Schwarz inequality to be true. Okay. Which says that if u and v are vectors in Rn, then the absolute value of the dot product is less than or equal to the product of the lengths of the vectors. Okay. Now this is a part where you can I won't require you to produce this. This proof is not trivial in any way, but I want to just give you a sort of a flavor of it to show why this is true. And what we're going to do is we're going to just prove this in one case where we're in 3 dimensions. Okay, when u and v are in R3. So let's talk about that. For this, we want, before we get, so here's our proof. We want to start out by knowing this fact that if A, B, C, and D are real numbers, then 2A, B, C, D is less than or equal to A squared, D squared, minus b squared c squared. Okay. Okay. And this is not a fact that you probably think about every day, and I don't either. But it can be proven just because from the following. So why? Well, because I said so, or because we know that AD minus BC squared is always non-negative, because anything squared is non-negative. And if we multiply this out, we get a squared d squared minus 2AD BC plus b squared c squared is greater than or equal to 0. And then we can take this middle term over to the other side, and we get this. Okay, so that's why. All right. So we're going to be using that. Now, look at the case n equals 3. We're gonna, if we start out, instead of writing this, and we're gonna really prove this is true if you square both sides. So if we look at the length of u squared times the length of v squared, this is going to be the dot product of u with itself, and this is the dot product of v with itself. So this is going to be u1 squared plus u2 squared plus u3 squared times v1 squared plus v2 squared plus v3 squared. Okay. Okay, and then we can multiply this out. It might be a little unpleasant, but there are really just two, there's going to be a total of 9 terms. If we take these two, and these two and multiply them together, we get u1 v1 squared plus u2 v2 squared plus u3 v3 squared. And then there are going to be some 6 other terms. We have plus u1 squared v2 squared plus u2 squared v1 squared plus u2 squared v3 squared plus u3 squared v2 squared plus u1 squared v3 squared plus u3 squared times v1 squared. Okay. And then this is where we're going to be using our fact here. In this first case, we're going to use, let A be u1, D be v2, B be u2, and C be v1. And so that this is going to be greater than or equal to 2 u1, u2, v1, v2. This will be greater than or equal to u2 times u2, u3, v2, v3. Now this is going to be greater than or equal to 2 u1, u3, v1, v3. Okay. And now we have that this, we're going to take this sum all together here. That's we're adding these, not multiplying. But if we take that, so what we're saying is that this thing, this quantity that I've circled, is less than or equal to this. Okay, and what is this? This actually reduces to u1 v1 plus u2 v2 plus u3 v3 quantity squared. Okay, if you multiply this out, it works. It works. Okay, take my word for it. And this, of course, is the square of u dot v. Okay, so then we take the square roots. And done. Right? Because we take the square root of this, we get the length of u times the length of v. And this is, again, we're taking the square root of u dot v squared. So we have to be a little careful. We know this is not u dot v, this is the absolute value of u dot v, because u dot v could be negative. All right? So that proves that. and then that allows, we know now from that we know for sure that that this quantity now will be between 1 and -1. Okay, and so now we can go ahead and well, we're almost ready to define the angle between two vectors. But let me just, for one real neat consequence of this is that we can prove the triangle inequality, which you may have seen before in other classes, which says that if you take any triangle, you know, the sum of any two sides is always going to be greater than or equal to the other side. Okay, and why is that? Well, it helps to write this as well. We'll get to this in a minute, but let's say we prove this. This is the vector form of the triangle inequality in Rn. So why does that hold? So here's a proof. Here's again a proof. Again, you won't be responsible for it on a test or anything, but you should probably see how it works, and it's actually going to be a little easier than the other case, the other proof. So u dot v is less than or equal to the absolute value of u dot v. Okay, sometimes they're equal, sometimes they're opposite, but this always holds. And then we know by Cauchy-Schwarz that this is going to be less than or equal to the length of u times the length of v. Okay, by Cauchy-Schwarz. Okay. Okay. All right. Now we multiply both sides by 2. Okay. And then we add a couple things. Then we add the length of u and the length of v to both sides. And I'm going to arrange it so that I'm adding the length of u on the left and the length of v on the right. So okay. So all we've done is added two quantities to both sides. Okay, and this should be still less than or equal to. Okay. And then we know is the fact that this is u dot u and this is v dot v. Okay. And then we use our distributive law and see that this is really just going to be u plus v dot u dot v. All right, because this will be u dot u plus 2 u dot v plus v dot v. And then over here, this is going to be the length of u plus the length of v squared. Okay. And if this, in fact, is going to be the absolute value, well, this is going to be the length of u plus v. Okay, and then again, you take square roots. And you're done. Okay, so that is the triangle inequality. And just to show you where this comes back to the actual triangle, if you call this side u, or the vector representing this side, and if v is the vector representing this side, we can call this vector u minus v. Okay. And the length of u minus v is going to be the same thing as the length of u plus negative v. Okay, because remember, subtraction is really just addition. And then we can apply the triangle inequality to this. This is the length of u plus the length of minus v. But the length of minus v you can easily check, but that's the same thing as the length of v, because you change the sign, you square they go away. The minus signs go away when you square stuff. So this is the length of u plus the length of v. Okay, so that's why this side plus this side is always bigger than this side. Okay, so that's how the triangle inequality works. All right, last page here. So now we officially define the angle between two vectors, two non-zero vectors in Rn to be theta, where the cosine of theta is u dot v times this. And we'll actually see that this actually agrees. What happens if we know the two angles are perpendicular to each other or orthogonal? Are they, then that means this is better to be zero. And we'll see why in the next video. We'll see why that is indeed the case. Well, we define, so once we define cosine, we can just say cosine, that theta is the inverse cosine of this quantity. So, for the last example, let's say we want to find the angle between these two vectors in R3. Okay, so if we call this u, and I call this v, we take the dot product, u dot v is going to be 1 times 3 plus 1 times 1 plus negative 2 times 4, which is 3 plus 1 minus 8. I think that's negative 4. The length of u is the square root of 1 squared plus 1 squared plus negative 2 squared, which is square root of 6. The length of v is the square root of 3 squared plus 1 squared plus 4 squared, which I think is 26, the square root of 26, right? 9 plus 1 plus 16, yeah. Okay, and so the cosine of theta will be negative 4 over square root of 6 times the square root of 26. This is approximately equal to negative 0.3202. Okay, and so theta, you take theta is going to be the inverse cosine of negative 0.3202, which is approximately 108.7 degrees. Of course, you want to use the make sure you're in degrees mode. Okay, on your calculator. Okay, a lot of material in this lecture, right? Let this all soak in. Maybe do a few of the homework problems and then take the mini quiz. Okay, so thank you. I'll see you next time.